Okay, next is momentum review. Again, quickly. So first of all, momentum is for a particle is represented by little p, small case p, and that's the mass times the velocity of the object. But this is for a particle, okay? And so now, as we are doing more complicated problems, we may have a system, distributed masses, so it's not a particle. In that case, we use capital case P, and the mass is big M to show that it's the system's mass. And the velocity here has to be only for the center of mass point. Because again, if it is not a particle, distributed mass, then not every point on the object has the same velocity, meaning same speed and same direction. So you can only use the center of mass point. So that's what we discussed before, like how to find this point, and then you can just define the motion of that center of mass point only. So I'm going to say this is a distributed mass. Okay, so we started with the momentum definition. Momentum, again, if you take a look at this equation carefully, it is a vector, first of all, right? And it has the same direction as the velocity vector. And it is really a scaled vector of the velocity vector by the mass. Mass is always positive, so that's why they always, P and V always points the same direction. But at the same time, again, it's a kind of a scaling factor is the mass. So when you multiply mass with the velocity, you will find the momentum. Just a quick reminder, the units using this equation, it is mass times velocity, so it's going to be kilograms meters per second square. There's no special unit, so this is the unit for momentum. I do not memorize it, I just think about what the equation is and I get it from there. Okay, so this is momentum, and we discussed Newton's laws, and the second law, Newton actually started with the momentum version of the second law. So we started with saying F equals to ma, right? And this is for, again, particle. Little m represents particle. This is a vector equation, so we split this into three pieces. We said for the x component, this is max. For the y component, this is may. And for the z component, this is maz. Right? And we can do the same thing for a distributed mass, so it's not a particle. And in that case, we said that we emphasize that this is being an external force, because the distributed mass, you may have internal forces within the system. It looks like there is a force, like it could be a tension force or explosion or something, and we've done some practices. So those forces becomes internal, so you do not put them in, but I'm gonna skip writing external because these sum of forces are external force. You need to know that, but in the equation sheet we emphasize it. Little m becomes capital M because this is for the system now, and the acceleration will be for the center of mass. So you do the same changes for each. Capital M for the system, and acceleration becomes center of mass acceleration. And again, for z component, capital M for the system, and this is the center of mass along the z direction. Okay, so it's nothing new so far, but how do we introduce momentum to this? So we know that P is equal to mv, and sum of F equals to ma. What is the relation between A and V? All right, so if I take the derivative of both sides of this momentum equation, what do I get? I do get ma on the right side, because dv over dt is acceleration, and dp over dt then is going to be sum of forces. So this equation becomes, for a particle, this was ma, but it is now also dp over dt. Again, this p is small because small case, because I'm writing it for a particle so far. Now we are going to use this and but write it for a system. So I'm making a capital P. This is for a particle. I'm going to say system or distributed mass. Okay, so now we have capital P. So once again, you can write this in three components. Okay, and P becomes also MV, but that V should be center of mass. So if you see a capital P, it's related to the center of masses. But what this equation tells you, so let's just split up first one to three components, dpx over dt, and then for y component, dpy over dt, and for the z, dpz over dt. So what this tells you is that if you don't have sum of forces, if sum of fx is 0 from the free body diagram, okay, that means if this is 0, then that means this is what? This is the rate of change in momentum, right? So that tells you there's no change. So px is constant then. Okay, what that means is initial and final pix equals to p final x. They are going to be the same. This is what a momentum conservation is. So in this case, momentum is conserved along the x direction. Okay, this is nothing you need to remember. You just need to understand the equation. This is Newton's second law here. Okay, this is the momentum version of the second law. And that's for the x components. So you're looking for the free body diagram, figuring out what is sum of fx. If it is 0, then, only then, px is going to be constant. That means initial and final are the same. So initial and final are the cases like something happens, maybe it hits the ground, it touches something else, okay? And some collision, some explosion, something happens. And so we are looking at right before and right after, initial and final cases, and we are saying the momentum doesn't change then, and because the sum of fx is 0. And then you can do the same thing, look at the y components and z components. If also these are 0, the momentum along y and z will also be conserved, and then you can write the same equations. After this, again, we will be using the momentum definition, which is mv center of mass. So for the x component, this is going to be x direction, for example, and you're going to get rid of the vector signs because the components are scalars, right? So you're using this, you're going to write this for initial case and also the final case. If you know that the object has in 3 pieces and the final case, so then you have 3 terms on the right side here, using this definition there. And initially, if it was 1 piece, then you have only 1 term, so you're going to write those things differently, and this mass also changes if you have now 3, if split into 3. So these are the problems that we are still working on, and I'm going to add a couple more today. So please check that understanding in today's class. And I'm planning to finish chapter 9 today because we are skipping most of the parts, but we will have a couple extra problems added, and I'm also going to add a center of mass problem just so after the break we refresh what we learned about that too. Okay.